Hello, everyone. It's a pleasure to have here today Laura Herold. Thanks a lot, Laura, for accepting our invitation. Laura is a Miller Fellow at the Johns Hopkins University in Baltimore, and before that, she got her PhD at the Max Planck Institute for Astrophysics in Germany. Laura's research topics are cosmological tensions, early dark energy, Bayesian and Frequentist approaches of parametry inference. Today, she will present the cosmological tensions and statistics, insight from Bayesian and Frequentist approaches. Laura, you can start, please, when you're ready.
Thank you very much for the very nice introduction, and thanks a lot for giving me the chance to speak at the CosmoVerse seminar series. Yeah, as I said, my talk is about cosmological tensions and statistics, and in particular, I want to focus on frequentist approaches, which are less common in cosmology, but have received increased popularity recently. As a small motivation, we have the 6-parameter lambda CDM model, which fits most cosmological data extraordinarily well. However, some tensions have appeared during the last years, the most famous being the one in the current expansion rate of the universe, H0, the Hubble tension. But there are many other tensions with less significance, for example, the tension in the amplitude of matter fluctuations, sigma 8. So from a theorist perspective, how to solve the tensions? The most common approach is to start from the 6-parameter lambda CDM model and add extra components or interactions. So build models of the type lambda CDM plus X, which are so-called nested models because they have a lambda CDM limit. Now, these models can have several additional parameters compared to lambda CDM. However, adding more and more parameters can lead to degrading of constraining power. And this itself can lead to an unwanted or even unknown dependence on analysis choices and priors. I also want to mention here that this is not only important, of course, in the context of tensions, but could also be interesting in next generation experiments, because although they will improve the data, they might need to introduce many additional nuisance parameters. So in this talk, I want to motivate the use of both Bayesian and frequentist methods, because they can give important insights in these cases below the detection limit. So in this talk, I want to start with the motivation of the use of both of these methods, starting with an example in the context of the Hubble tension, where I want to talk about the early dark energy model. And later, I want to talk about neutrino mass constraints and about late time dark energy. So basically motivate why to use frequentist methods. In the second part of the talk, I want to give a condensed introduction to frequentist parameter inference, particularly the profile likelihood, which has received increased attention recently. So answer the question how to construct frequentist parameter constraints. However, the profile likelihood relies on the assumption of the asymptotic limit. So in the last part of the talk, I want to present our recent paper where we check for CMB data whether these assumptions hold and the profile likelihood method can actually safely be used. So basically answer the question, when is it safe to use the profile likelihood? So I want to start with the case study of the early dark energy model and the Hubble tension. So as most of you know, the early dark energy model is a proposed solution to the Hubble tension. And in its simplest form, it is modeled by a scalar field with an axion-like potential of the shape 1 minus cosine to the power of n, where this index n is typically fixed. So this model introduces 3 extra parameters compared to lambda CDM: the mass, the decay constant, and the initial value of the field. Now, it is common to compute from these particle physics parameters m, f, and theta I, the phenomenological parameters FED, CC, and theta I, where FED is the maximum fraction of early dark energy at the critical redshift CC, and theta I is again the initial value of this scalar field in the potential. To solve the Hubble tension, one typically aims for a fraction of 10% of early dark energy at its maximum. So can early dark energy solve the Hubble tension? The answer is yes, if one considers the following data sets. So typically one considers Planck cosmic microwave background data, baryon acoustic oscillation data, supernova data, and the direct measurement by the Schu's collaboration. And using these data sets, one finds about 10% of early dark energy and high values of H0 that are consistent with the Schu's direct measurements. So one could say that there's a preference for early dark energy in these data sets, and early dark energy can solve the Hubble tension. However, if one if one excludes the shoes direct measurement from the data sets, and in this example includes weak lensing data from DS kits and HSC, one finds tight upper limits on the fraction of early dark energy. But in general, one finds that if one does not include shoes in the analysis, typically one finds no preference for the early dark energy model. So is early dark energy ruled out? Several authors have pointed out that volume effects could impact the constraints on the early dark energy model. So what are volume effects, also known as prior volume or projection effects? To illustrate this, I picked this example from a paper by Adria Gomez-Valent, where they consider a toy experiment that is sensitive to two parameters alpha and beta, and gives this black posterior, which has this Gaussian part and this non-Gaussian extension. And now consider a second experiment, experiment 2, which is only sensitive to alpha and gives this blue posterior. Now, let's assume we are more interested in parameter alpha, so it might make sense to look at the 1D marginalized posterior of alpha, which is simply obtained by integrating over beta. And this gives this, for experiment 1, this black contour. So most of the posterior mass are at alpha equals 0, where there's this large volume in beta. And the blue posterior for experiment 2. Now, although alpha equals 0 fits the data equally well as alpha equals 5, alpha equals 5 is outside of the 2 sigma confidence interval for this experiment 1. Only if one combines experiment 1 and 2, one finds a good measurement of both alpha and beta. So it might seem counterintuitive that in the 1D marginalized posterior, one finds like a 3 sigma tension between experiment 1, experiment 2. But if one looks at the 2D posterior, it's very clear what is going on. But in cosmology, we have often large dimensional parameter spaces where it's difficult to visualize things like this. So prior volume effects appear if the posterior is influenced by the prior volume. And reasons for this can be that the data is not constraining enough. That means the likelihood is very flat. And this happens for models with many parameters. Moreover, the parameter structure of the model can generate large volume differences. And this often happens with nested models. So for example, in the case of the early dark energy model, one has these 3 parameters, the fraction, so the amount of early dark energy, and the 2 parameters that describe the model more closely. Now, if the fraction of early dark energy goes to 0, so no early dark energy, basically the 2 other parameters are completely unconstrained, and one recovers the lambda CDM limit, but with 2 extra dimensions. And integrating out or marginalizing over these 2 extra dimensions can lead to a preference for the FED of 0 limit in the marginalized posterior. So one idea to probe these prior volume effects is to use the profile likelihood, since by construction, it does not depend on priors. So the profile likelihood is a method from frequentist statistics, which is used to construct parameter intervals. And it's based on the likelihood or on the chi-square, which for a Gaussian is simply -2 log likelihood. And one can construct the profile likelihood for some parameter of interest y by fixing y to different values and then minimizing the chi-square or maximizing the likelihood with respect to all other parameters. So instead of marginalizing over the nuisance parameter, one profiles or minimizes over the nuisance parameters. And now the graphical profile likelihood method can be used to construct confidence intervals. So one can simply read off the 1 sigma confidence interval at the intersection of the profile likelihood with delta chi-square equals 1. So this gives a 1 sigma confidence interval. And the same for 2 sigma at delta chi-square equals 4, and so on. However, this profile likelihood construction, although it's very simple, is only valid in the asymptotic limit, and I will discuss this in the last part of the talk. So coming back to early dark energy, using MCMC posterior to constrain this model with Planck and Boss data, one finds these tight upper limits and a low H0. But using the profile likelihood, one finds a high fraction of early dark energy and a high H0, which is consistent with shoes within 1.4 sigma. So this is one example where Bayesian and frequentist approaches give different results. And this can happen because the likelihood is not very constraining, and this is basically an effect below the detection limit. But using both approaches can point to prior dependence and can help to explore these things. But on a positive note, with more data, both approaches should eventually agree. And possibly for the early dark energy model, we are maybe already in the limit of this large data where both approaches agree, because in this paper from last year, it was shown that if one uses the alternative Planck NPipe and ChemSpec pipeline, which uses different analysis choices and more data than the standard click likelihood, this gives smaller lambda CDM residuals and tighter constraints on the fraction of early dark energy. So this is the red line here, which prefers low amounts of early dark energy and a low H0, which cannot resolve the Hubble tension. So here Bayesian and frequentist approaches agree, so maybe it's already in the limit of the large data set, and we need to be more creative in creating solutions to the Hubble tension. So for the early dark energy model, I only talked about the profile likelihood, but actually there's much more to frequentist parameter inference, and I want to give a short overview about that here. To fix the notation, of course, the central quantity here is the posterior, which is the probability of the model parameters theta given some data x, which is given as likelihood times the prior. And there's often a lot of discussion about the prior, which encodes prior information and beliefs, because if the data is not very constraining, so the likelihood is flat, then there can be a strong inference from the choice prior. Now, credible intervals can simply be constructed by integrating over the posterior and requiring that this is equal to the desired confidence level. And the method to obtain posteriors is the Markov chain Monte Carlo, so usually MCMC. Now, if the model does not only depend on one parameter mu, but also on nuisance parameters mu, one can obtain the 1D posterior by marginalizing, so integrating over the nuisance parameters. And the interpretation of this interval can then be phrased as, given the data and the priors, my degree of belief that the parameter theta is within this interval is 1 minus alpha. So the Bayesian interval is a statement about the degree of belief, and it actually assigns a probability to the parameter, which is not possible in frequentist statistics. Now, in frequentist statistics, the central quantity is the likelihood. Priors are not necessary, but in principle, they can be included by multiplying them as additional likelihoods. Now, the interpretation is different. The true, and can be phrased as follows, the true value of the parameter is contained in the interval of fraction 1 minus alpha of the experiments. So the defining property is the coverage here. So does the interval cover the true value of the parameter? And one says that if less than 1 minus alpha of the intervals contain the true value, then the interval undercovers. And if more of them include the true value, then it's said to overcover. And the method to construct confidence intervals that guarantee this coverage is the so-called Neumann construction, which in the limit of a large data set simplifies to the profile likelihood. And in the next few slides, I want to give a short introduction to this Neumann construction and illustrate how it simplifies to the profile likelihood construction in the case of a Gaussian probability. So the goal of this construction is to construct a confidence interval for some parameter of interest, which we call mu here, which could be, for example, the Hubble constant, under some data vector x, for example, the CMB power spectra CS. And then the Neumann construction is also known as inversion of hypothesis test, because it constructs a hypothesis test for a given confidence level alpha for all values of the parameter of interest mu. And this is done by defining a so-called test statistic, which is simply a function which determines whether a given data set is deemed consistent or inconsistent with a value of mu. So whether a given data set is rejected or accepted. And then we can determine the interval by integrating over the probability of this test statistic given the parameter of interest and choosing some ordering rule, where an ordering rule could be requiring a central confidence interval or an upper or lower limit. And I illustrate this here on the right-hand side. So for some choice of the parameter of interest mu1, one uses the test statistic to define which data sets are accepted as being consistent with the hypothesis that this is the true value of the parameter and which ones are rejected. And then one repeats this procedure for different values of mu to define an acceptance region and a rejection region. And this acceptance region is also called the Neyman band. And now the last step that one needs to do is to actually observe the data. And from the observed data, one computes a test statistic of the observed data. And now the interval in mu is defined as a set of all hypotheses which are not rejected by this data set. And this is simply given by the intersection of this band with the Neyman band. So simply the projection on the y-axis. And now because basically to illustrate this better, I want to show this for a very simple example for just the Gaussian probability. And I want to show this for the simplest choice of test statistic, which is just using the maximum likelihood estimate. So basically the best fit value of the parameter of interest, which in this case is the mean of the Gaussian. And to construct the Neyman band now, we simply solve this integral for different values of mu and require a central interval, which gives these red and blue shaded areas, which is 1 sigma and 2 sigma confidence intervals. Now here, since it's very simple, we know the probability of this test statistic given the parameter of interest, but in general, this is unknown and needs to be obtained from generating many mock realizations of the data and then computing the test statistic for these mock realizations of the data and histogramming over them. And this would give an estimate for this probability density. And now again, the last step is to measure some value of this test statistic t in real life, basically, where here we say we measure mu hat being 0.25. So we look for the intersection of mu hat being 0.25 with this Neyman band, which then gives intervals in the parameter of interest. Now, in the slide before, we used the simplest choice of test statistic, but a very common choice is actually to use the likelihood ratio as a test statistic itself. So the likelihood ratio is simply -2 times log the likelihood of the data given some parameter of interest as indicated in the index, normalized by the likelihood of the data given the maximum likelihood, so the best fit mu value. And this is nothing else but the data chi-square for a Gaussian. So now we can again construct the Neyman band by solving this integral. And the interesting part about using this test statistic now is that this gives a constant Neyman band. So the red and blue are the 1 and 2 sigma confidence regions, which before were these diagonal lines, but now they're actually at constant cutoff values of basically delta chi-square equals 1 and delta chi-square equals 4. And now what changes is when you actually measure a data set and you insert this in the likelihood ratio test statistic, the data does not trace a straight line anymore, but it actually traces a parabola for a Gaussian distributed parameter. And this, of course, resembles the graphical profile likelihood method. So we get basically constant cutoff values in chi-square, and the data traces a profile, and the confidence interval is given by the intersection of these cutoff values with the profile likelihood. And so again, for a Gaussian, the Neyman construction simplifies to the graphical profile likelihood method of looking for this iso likelihood contours. But actually, this generalizes in Wilks' theorem, which states that actually in the limit of a large data set, not only for a Gaussian, but in the limit for a large data set, this likelihood ratio is the same for any parameter mu, and it follows a chi-square distribution. And this theorem guarantees correct coverage for the graphical profile likelihood method. And there's actually, this is illustrated here on the right-hand side. So if we draw mocks from a Gaussian, which are these gray points on the line, we see that the histogram along the x-axis is a Gaussian since we draw from a Gaussian, but the likelihood ratio test statistic actually follows a chi-square distribution. And this illustrates why the graphical profile likelihood method gives correct coverage, because it's well known that a chi-square of 1 contains basically 68% of the MOCs, and the chi-square of 4 about 95% of the MOCs. And then there's a second theorem that is important in this context, which is Wall's theorem, or also called Wall's curve, which states that in the asymptotic limit, actually this likelihood ratio test statistic follows a parabola, which can also be seen here on the right-hand side. So the MOCs closely lie on this parabolic line. So the example before was basically the simplest example one could think of, but the next complicated example one could think of would be a Gaussian at a boundary. So we require that the mean of the Gaussian has to be larger than 0, for example, because mu could be a mass. And already this small restriction makes the construction much more complicated. And I also want to go through this now quickly, because it's relevant when we talk about neutrino mass constraint, because then it's the case where some of the neutrino masses can only be larger than 0. So if one uses the simplest test statistics, so just the maximum likelihood estimate of mu, and one solves this integral, one could choose a simple ordering rule, like a central interval or an upper limit. However, it turns out to be very convenient to use a more complicated ordering rule, which is based on the likelihood ratio. So this likelihood ratio is the same as before, but one requires that mu hat has to take on physical values. So if mu hat is larger or is smaller than 0, it's set to 0, and mu hat larger than 0, one chooses mu hat. And this is the famous Feldman-Cousins construction, and it gives bands that smoothly transition between an upper and lower limit. So if mu is close to 0, one gets basically here upper limits. But if mu hat is much larger than 0, then one would get central confidence intervals. Now one can, of course, simply use this likelihood ratio as the test statistic itself and solve this integral again. And now we find for values that are far away from the physical boundary in 0, we find again these constant cutoff lines. But there are some corrections for small values of mu, which come from this boundary and the fact that we only allow this mu hat to take on physical values. And this resembles the boundary corrected graphical profile likelihood method. So again, one can just compute the profile likelihood of the data, but this time use the corrected boundaries here. And now in the asymptotic limit with the boundary, Wick's theorem does not hold anymore, but one can adapt the graphical construction using the Feldman-Cousins or using the likelihood ratio as a test statistic and still guarantee the correct coverage. Moreover, the Wall's curve is now modified, and only for values larger than 0, the MOCs follow a parabola, and for values smaller than 0, the MOCs lie on this straight line. Before I go back to physics, I want to discuss one more complication, which is the presence of nuisance parameters. So before we used the likelihood ratio as a test statistic, but in the presence of nuisance parameters, one used the profile likelihood ratio test statistic. So if there are nuisance parameters nu, one uses the conditional maximum likelihood estimate. So for each value of mu, basically as before when computing the profile likelihood, for each value of mu, one minimizes the chi-square or maximizes the likelihood and obtains the best fit values of the nuisance parameter for each choice of mu. And then the normalization is again using the global maximum likelihood estimate. So in a sense, the main difference between Bayesian and frequentist statistics is or can be seen as the treatment of nuisance parameters, where in the Bayesian case, one marginalizes or integrates, and in the frequentist case here, one profiles or optimizes over the nuisance parameters. So how to compute a profile likelihood? The main ingredient is to have an efficient minimizer. There are many public codes available now, and with our recent paper, we also made our code available, which is a very simplistic simulated annealing-based code. And to conclude the second part of the talk, I have a table which compares the frequentist and Bayesian approaches. So of course, the Bayesian approach is based on the posterior, which is proportional to the likelihood times the prior, whereas on the frequentist side, when central quantity is just the likelihood. Then nuisance parameters are marginalized over in the Bayesian case. So the Bayesian interval identifies volumes in parameter space that fit the data well, whereas in the frequentist case, nuisance parameters are minimized or optimized over. So one identifies points that fit the data best. So one problem in the Bayesian case that we discussed in the context of early dark energy is that if the data is not constraining, enough prior dependence or prior effects can appear. But frequentist intervals can have the exact opposite problem. They could prefer a cosmology with very small parameter volumes, so very finely tuned parameters. But on a positive note, in the limit of a large data set, both of these approaches should agree. So in the last part of this talk, I want to discuss our recent paper in collaboration with Elisa Ferreira and Lukas Heinrich, where we asked the question whether the asymptotic limit holds in cosmology and one can safely use the simple profile likelihood construction. And for that, we do that for Plick light data and 3 cosmological models. So the motivation for this project is that there's a Neyman construction, which is the most general construction, and it guarantees correct coverage in every case, but it's numerically very expensive because it requires many evaluations of the likelihood. And then there's the graphical profile likelihood method, which gives correct coverage only in the asymptotic limits and the limit of a large data set. But the assumptions of this asymptotic limit are rarely checked, and up to our knowledge has never been checked in cosmology context. So here we want to probe the distribution of this likelihood ratio test statistic explicitly and check whether the asymptotic assumptions hold. And which means that the graphical profile likelihood can be safely used. So for that, we generate mock realizations of Planck light data, so the Plick light likelihood, and ask the question whether it is consistent with Wald's curve or the modified Wald's curve in the case of a boundary. And for that, we consider 3 different cosmological models: the lambda CDM model, lambda CDM with the sum of neutrino masses as the free parameters, and the W0 CDM model with the equation of state of dark energy as a free parameter. And we do this with these 3 steps. So first, we generate mock Plick light data, where we use the Planck 2018 best fit cosmology as our ground truth cosmology for generating the mocks. And because the Plick light likelihood is the simple correlated Gaussian, it's easy to generate mock data of it. So basically, we assume the Planck best fit cosmology as the cosmology. We compute the CLs using class and take the covariance from the public Planck data. Then in the second step, we compute the maximum likelihood estimate of the parameter of interest, mu hat, and we compute the profile likelihood ratio test statistic. And then as a third step, we verify whether these mocks follow the expected Wald's curve, which they would if they are in the asymptotic limit. There's one big caveat here. So of course, this is no proof that the asymptotic limit is reached because we only do a checks for one fiducial cosmology, and in principle, this should hold for any cosmology. So as a first check, we want to check whether Wilks and Wald theorem hold in lambda CDM. So we choose as our parameter of interest, we choose the Hubble parameter, little h. And in our first step, we consider no nuisance parameters, which means we fix, when we compute the likelihood ratio, we fix all nuisance parameters to the ground truth. And we generate 250 mock realizations and compute the maximum likelihood estimate and the likelihood ratio for each of these mock realizations. And this is what we find. So each of these markers is one of the mock realizations. And we plot them as a function of the likelihood ratio and the maximum likelihood estimate of h. And we find that h hat follows a Gaussian and the likelihood ratio follows a chi-square. And in this 2D space, all the mocks follow Wald's curve, which would be expected in the asymptotic limit. And we repeat this check for all 6 lambda CDM parameters, and we find good agreement between the distribution of the mocks and this Walls curve. As a second check, we want to check how this depends on nuisance parameters. So first, we only vary one nuisance parameters, the cold dark matter density. And we generate 3 sets of mocks with 3 different values of omega CDM. And then when we compute the likelihood ratio, we have to profile, so optimize over the value of omega CDM. But also in this case, we find that the mocks for all 3 different values of omega CDM follow closely Walls curve. Now, in the final check for the lambda CDM model, we want to vary all nuisance parameters. So we let omega CDM, omega baryon, AS and NS, so the amplitude and spectral index of the primordial power spectrum, vary in the fit, and we profile over these parameters. But we fix the reionization optical depth and A Planck, which is the nuisance parameter of the Planck light likelihood, since they are fully degenerate with AS, since we only use the Planck light likelihood. And even when leaving all nuisance parameters free, we find that all the mocks follow closely Walls curve. And in light blue, you can see what happens if instead of inserting here the ground truth value of, ground truth of mu, we inserted an alternative value for mu, where then one expects that the mocks follow the non-central chi-square distribution, which is also in good agreement with the mocks. So for all the checks we did in the lambda CDM model, we find good agreement with the predictions of the asymptotic theory given by Wilks and Wald theorems. And this indicates that the graphical profile likelihood method gives correct coverage. And again, of course, this is no proof and is only an indication. So using our knowledge, we can simply use the graphical profile likelihood method to constrain H now in real life. Basically, for that, we consider 3 different data sets: the Planck light likelihood, the Planck likelihood, and Planck plus baryon acoustic oscillation data from 6TF, SDSS, and BOSS. And for all of these data sets, we find good agreement between frequentist and Bayesian constraints. So yeah, basically for the lambda CDM model, we find very good behavior and indication that this is consistent with the asymptotic regime. So the second model we wanted to look at is lambda CDM plus the sum of neutrino masses as a frame parameter, where we know from neutrino oscillation experiments that neutrinos have to have mass, and the sum of neutrino masses need to be larger than 0.06 electron volts. So this is a natural extension of the lambda CDM model. And curiously, Planck data shows an apparent preference for vanishing or even negative neutrino masses. So this plot here on the right-hand side is from an old, like 2013 Planck collaboration paper, where they find that using profile likelihoods, the minimum of the profile likelihood is basically if you extrapolate to very negative masses, it's at very negative neutrino masses. But this has already been also been pointed out in the more recent literature. And moreover, the recent DESI results give the tightest cosmological neutrino mass bounds when combined with Planck, which give an mu of smaller than 0.072 electron volt, getting closer to this lower limit by neutrino oscillation experiments. And this makes this model interesting to study, because if this trend continues, this can lead to tension with the lower limit from neutrino oscillations. So we do our checks on this extended lambda CDM model. As a parameter of interest, we take the sum of neutrino masses, and as a first step, we fix all nuisance parameters and generate mocks with a fiducial cosmology and a sum of neutrino masses of 0.06 electron volts. And this is what we find. In the case where we fix all nuisance parameters, we find good agreement between the Walls curve and the mocks. Now, if we let all nuisance parameters free to vary, we find a different picture. So now, since all the nuisance parameters vary, the width of the parabola is wider because we have a basically larger error on the determination of mu. And we find a large scatter in the mocks, which could be due to the more complex model, which has now 5 nuisance parameters, or it could also be intrinsic to the likelihood, which would also point to a deviation from the asymptotic limit. But taking apart the large scatter, the shape seems to be consistent with the Gaussian near a physical boundary. So here in pink, we mark all the MOCs that have a neutrino mass below 0.005 electron volts, or basically prefer zero sum of neutrino masses. But what this means is that it indicates that the boundary corrected graphical method would give correct coverage because the distribution seems consistent with the Gaussian near a boundary. So using this knowledge, we use the boundary corrected graphical profile likelihood method to constrain the sum of neutrino masses. So now the 2 sigma acceptance region is not a constant anymore with a constant cutoff of 4 in this case, but it depends on the data and on the value of mu. So what I mean by that is the shape of this cutoff here depends on the width of the parabola, so on the 1 sigma, and it depends on the value of mu. But again, then the constraints can be obtained by the intersection of this cutoff with the profile likelihood. And in general, we find that the frequentist constraints give even tighter constraints on the sum of neutrino masses than the Bayesian constraint. But in general, they are in good agreement, at least for the Planck and BAO dataset. So using the profile likelihoods, we confirm the apparent preference for vanishing or even negative neutrino masses. Because if we extrapolate the profile likelihoods basically to negative neutrino masses, we find that the best fit values are always in the negative forbidden regime. And a few, maybe 1 or 2 weeks before our paper came out, this paper also explored the sum of neutrino masses using the profile likelihood. And they found that using actually an alternative Planck pipeline, which is called the helipop pipeline, this relaxes the bounds and actually reduces this apparent preference for the negative neutrino masses. And moreover, allowing for dynamical dark energy also relaxes these bounds. So it's definitely too early to speak of attention with oscillation experiments, but it's still very interesting to see what will happen with these neutrino mass constraints. So as a last model, we considered the W0 CDM model with a constant equation of dark energy as a free parameter. Now, since the new DESI results, there's more attention to more complex models of dark energy than just a cosmological constant. And here we use the next complicated model of dark energy, which just equation of state of dark energy as a free parameter. So now no time evolution, but using W0 as a free parameter. And this parameter is restricted to be larger than -1/3 because this is where the accelerating regime ends. Now we want to probe Wilks and Wall's theorem in this model. So we take W0 as a parameter of interest, and we fix all nuisance parameters to the ground truth and generate MOCs with a cosmological constant. And we find that these MOCs closely follow Wall's curve if we fix all nuisance parameters. However, if we do the same with 5 varying nuisance parameters, we have to profile over in the likelihood ratio, we find a first indication that the asymptotic limit might be violated. So it seems like the distribution of these MOCs show a slightly bimodal distribution with less MOCs in the cosmological constant regime and more towards the side. And moreover, the Wall's curve seems to be not a good description of the MOCs, and they seem to be bunched here at the low values. So this indicates a violation of the asymptotic assumption. There's actually one more check we did for all the models, which I haven't presented in interest of time for the other models, but I will show here because it's also an indication that the asymptotic limit is not reached. We analyzed the so-called Asimov dataset, where the Asimov dataset simply denotes a mock realization of the data that corresponds to the ground truth without any noise. And if one analyzes this ground truth data, basically one would expect a parabola in the asymptotic limit, but here we find this very asymmetric shape. So this indicates that in this case, for this model and these data sets, so the Planck light data set, the graphical method might not give correct coverage, and the full Neyman construction should be used, which is beyond the scope of this project. So regardless, we want to use the graphical profile likelihood method to get an indication of the confidence interval, although they mightn't give correct coverage. So we find that the profiles with Planck data alone prefer equation of states that are much smaller than -1, but adding BAO shifts W0 back to -1. Also, I want to point out that the profile likelihood is actually far away from the maximum likelihood estimate for Planck, and Planck light data are not well fit by parabola, so might also be an indication that the asymptotic limit is not reached. Regardless, we find good agreement between the Bayesian and the approximate frequentist constraints. So to summarize this last part of the talk, basically care needs to be taken in also in the frequentist analysis. Our tests for the lambda CDM model indicate that the asymptotic assumption holds, and this means one can safely use the graphical profile likelihood method. And for the lambda CDM model with the sum of neutrino masses as a free parameter, the tests indicate that this is consistent with a Gaussian near boundary. So one can use a boundary corrected graphical method or Feldman-Cousins method. And for the W0 CDM method, the tests indicate a violation of the assumptions, and one should use the full Neyman construction. However, of course, in practice, it is very impractical to always test the asymptotic assumptions in practice. So what one typically does is to simply assume that the asymptotic limit holds and acknowledges that the coverage might not be given. So to summarize, frequentist and Bayesian methods are complementary. They have different advantages and different problems. Just to name a few keywords, there's fine-tuning or coverage and prior effects. But I think using both can give interesting insights. We discussed early dark energy and neutrino masses and late-time dark energy. And in the last part, we discussed frequentist coverage and basically probe whether the asymptotic assumptions hold and whether one should use a boundary corrected or normal graphical profile likelihood method. Thank you.
Thank you so much. Very nice talk. Adam?
Oh, hi Laura. That was a great talk. Very interesting. And my question actually, it was something that came up very early in your talk when you were thinking about these different ways to look at likelihoods and analysis. It was actually more about early dark energy and differences in data sets. I think at one point you showed whether you used local H0 was included in an analysis with early dark energy or not. I guess my question to you is, when is it appropriate, or how would you decide whether to use which data sets? Because, in principle, just in the most general sense, one could have a piece of data that provides, some new window into something in your model that, you wouldn't see without it. Or, put another way, in this case, you could have local H0 in there and, would give you different results. And maybe it's something within the CMB data itself, which is in tension. And so my question is, since you've thought a lot about different likelihoods, what are sort of your views of when and which data to use when looking at tension?
Yeah, I think your question when to combine or not to combine has been discussed very extensively in the community, because it seems like for most of the models, if you include the choose H0 prior, basically, you find, of course, much higher values of H0. But then the question is, what if you're combining two data sets that are in tension? Of course, you will always find something in between, but it could worsen the fit to your data. So I think the view that most people have is that if you have two data sets and within the model that you look at, these two are in tension, they should not be combined in an analysis of this model. That this could be your lambda CDM model, and your EDE part of the parameter space is very small parameter volume. So if you look at some marginalized posterior, you could have some apparent tension, but there's actually this small extension that has very tiny volume, but it actually fits all data sets very well. But I think it's very difficult to find in which situation one is if one just runs basically one MCMC. So I think, yeah, using different probes to try to understand what's going on in the likelihood surface is important. I'm not sure if this answered the question.
Yeah, I mean, it does. I think, you know, like in this specific case, you know, if one used an EDE model and local H naught, and let's say, you know, the real tension was between, I'm just making this up, but high L and low L CMB, for instance. You know, if EDE was the right model, you know, that might reveal actually in the EDE model that the internal tension is between two parts of the CMB. And so, you know, if you're deciding a priori which data sets to include, then it seems like you would be blind to that potentially. But
yeah, I see what you mean. Yeah, I think there's always some subjectivity, which data set one trusts and which one not, and which one to include from the start. But yeah, I guess the only way is to basically run the analysis with different settings. And if something weird shows up, I guess this is an indication of things that you were pointing out.
Okay, thank you. Erwin?
Hey, Laura, thanks for a nice talk. So what confused me is Wilkes' paper, right? Like it seems that he arrives at an equation that sort of says the, you know, profile likelihood ratio is Gaussian up to small corrections that are 1 over the square root of n, where n is the size of the sample, right? You know, so if you want to diagnose whether or not the asymptotic limit applies or not, you could just look at the profile likelihood ratio and then see if that's close to Gaussian. You know, why do you need all the mocks? That's the question. And I have a comment. The comment also is basically when W0 becomes very negative in the WCDM model, and it's typically for omega m of 0.3, you find a turning point in the Hubble parameter at very low redshift. It's easy to prove this. So the problem for Planck, because they prefer a slightly lower W0 value, right? It's actually quite low. And we looked at your profiles, right? They seemed they were like almost -2, or, you know, W0 could be very close to -2. Then you would have a turning point in the Hubble parameter, and that violates the null energy condition. That's just a comment, right? So if we can focus on why can't you just basically, the question is, why can't you just basically look at the profile likelihood ratio and say it looks close enough to Gaussian, and maybe this is a good approximation to use delta chi² = 1.
Yeah, so the thing is, if you just look at the profile likelihood of the data, you're only looking at one specific data set. So basically, you're just looking at one of those mocks. But Wilkes' theorem is a statement about the distribution of T, so the likelihood ratio. So if you just look at the profile likelihood and say, well, it looks Gaussian, you don't know if this is just a coincidence because you're looking at one specific data set. So basically, when you use a data set and you construct the profile likelihood and it looks Gaussian, you know, you don't know whether basically your cutoff values are constants or whether they have a weird shape. Basically, the answer is no. You cannot just look at the profile likelihood of the data because it only tells you something about the shape of the likelihood using the real data set. Moreover, it doesn't tell you anything about the shape of your cutoff values. To obtain the shape of the cutoff values, you either have to assume some probability density or you have to compute mocks with basically in this picture different values of mu hat.
Right, but where are the cutoff values in Wilkes' paper? You know, where would we find the mocks in Wilkes' paper? You know,
right. I mean, Wilkes' paper is, yeah, since
I know it's a paper from almost 100 years ago.
1937. Yeah, it just assumes basically the central limit theorem, and then it assumes we know the probability density, and then everything is super nice.
Right, so they fix the probability density. The whole thing is kind of very circular, right? Wilkes' theorem, right? Because you seem to put in the, you know, the large sample limit that's put in, and then maybe the central limit theorem. You know, everything is effectively Gaussian from the beginning. You get out that your profile likelihoods are Gaussian, and then you map that over into a chi-squared distribution, and then you essentially integrate that guy, which is completely equivalent to just integrating a Gaussian profile likelihood.
Right.
Mathematically, it's equivalent, right?
Yeah, exactly. So as you said, this is all in the Gaussian limit, and then everything is nice and easy and can be done analytically. So I think, so your comment was about omega CDM?
Yeah, if we can have just a quick look at your profiles, your W zeros. Yeah, so we can see that your MLEs are very low, right?
Yeah, so I also like, you're completely
They're
right.
-2, right? And if omega m was
Yeah.
0.3, then that would be -1.5. Anything lower than -1.5 gives you a turning point and a violation of the null energy condition.
Okay. Yeah, I mean, what we found is that you really hit the degeneracy between W naught and H naught, because if you just look at Planck data, these two are perfectly degenerate. So the constraints are very, are not meaningful. They can only be used to construct upper limits, basically. But okay, yeah, probably interesting about the turning point.
Right. That would tell you that there's something wrong somewhere, right? You shouldn't violate the null energy condition.
I guess the only sensible thing is to look at this model using Planck and BAO. Otherwise, you get into unphysical regimes.
Right. Okay. I'll send you a reference. Okay. Thanks very much.
Thank you.
So let's thank Laura again. Thank you.
Thank you for having me.